It's 7:01. I am going to get started. So today I got the adapter, so it's hooked up, but I'm also ordering a new battery pack so the computer actually can store enough juice for at least one class. And no, the division is not paying for it. I'm paying for it. Are there any questions from the discussion on Tuesday, the lecture on Tuesday? Are there anything that you want me to clarify? Okay, are you guys ready? Okay, so are there any questions from Tuesday that you guys might want to bring up? Yep.
So how we talked about, with the 3-bit example, unsigned can go from 0 to 7, and then signed would be from -4 to 3.
Okay, so let me bring up the number wheel, because this is from the other class. This is from the Monday Wednesday class, but the wheel part should still work. So there we go. Okay, so this is a 4-bit instead of a 3-bit, so you can see how it is just a little bit bigger. So the question is?
So in this example, signed would go from -8 to 7, and then unsigned would go from 0 to 15. Maybe this is like getting ahead, but how would the computer know the difference between signed and unsigned?
The computer doesn't need to know. Okay, so so with all the carry, look ahead, adding, adder, and subtractor, it doesn't really care, whether you're dealing with a signed value versus an unsigned value. Okay, because there's no need to. The adder circuit will work whether you're dealing with signed or unsigned. Okay, let me explain why I said it would work in either case. Okay, so we'll just pick some examples here. I have to make sure that it's remaining within the range. So I'll just ask this question. I'm going to borrow this slide if it's okay with you guys, because from the perspective of the recording, it doesn't really matter whether the number wheel is coming from this class or the other class. So I'm just going to borrow this number wheel here. So we want to do okay, so let's see, go back to end mode. So we want to, let's say add -1 to -2. Okay? So this is what I want to do. From the value perspective, I'm dealing with signed values, and one signed value that I'm trying to add is -1, and the other signed value I'm trying to add is -2. Is that okay? So when you look at the number wheel, you can see how these two are represented. -1 is represented by 1, 1, 1, 1 as a binary number, and then -2 is represented by 1, 1, 1, 0 as a base 2 number, or base 2 representation. Is that okay? All right. So we're going to carry out the binary addition, because we already know that in base 10, -1 plus -2 is -3. So the question is, if I use the binary representation of -1, and I use the addition logic that we have been talking about already to add -2 to that representation, use the base 2 representation of -2 and add it to the base 2 representation of -1, I should end up with the representation of -3. Is that making any sense? So we want to confirm that, okay? So now we have 1, 1, 1, 1, which is representing -1, plus 1, 1, 1, 2, which is representing 2. And if you want to, we'll use a subscript of 2 just to emphasize we're not dealing with base 10 numbers. We're not dealing with 1,111. We're dealing with 1111 as a base 2 number. And then we'll do it in the usual 2-stage. We put a 0 here because this is not a part of the longer addition. So carry in can be 0. Okay, we can assume it is 0. So now we just do all the math. 1 plus 0 is 1. 1 plus 0 is 1. And neither is giving me any carry. So the carry to this part here is going to be a 0. Is that okay? 1 plus 1 is a 0, but it also has a carry. So we put a carry in the next column right away. 0 plus 0 is just a 0. Okay. 1 plus 1 is a 0 with a carry. And 0 plus 1 is a 1. The same thing over here. 1 plus 1 is a 0 with a carry. 0 plus 1 is a 1. Okay, so our sum is actually this number here as a base 2 number. So it's 1101, and then you look at the number wheel, and what is 1101 representing as a signed value? -3. So from this perspective, until we really need to know whether we are representing signed or unsigned values, we just say, oh, we are just given a whole bunch of bits, and we know how to add and subtract a bunch of bits. That's all we need to do. So we don't have to distinguish between whether we are dealing with signed or unsigned values. Is that okay? Yep. Go ahead. Huh?
Negative, what about -8, -3?
Okay, so when it is out of range, then we have a problem. Okay, so when you add the values and it is out of range, then we have a problem. Because you cannot fix that problem because you only have this many bits to play with. So you know, if the result of an addition or the result of a subtraction is out of the range, then you just have to deal with it. You know, you just don't have enough width to represent the values that you need to represent.
So since the range isn't in half, then every time you add, it overflows. And overflow causes you to only keep the other numbers, and those numbers always give you the sum.
Right. So before the calculation, you really need to check and say, okay, is this calculation going to exceed the range that I can use? So this brings up, you know, I'm going to use a new slide here. Does anyone want to go back to that slide, or is it okay to open a new slide? You want to go back to the old one?
Right?
I just have a quick question as to what happens to the carryout.
Okay, so carry out, that's a good question. It's a good, legitimate question. So the carry out, which is this one bit here, okay, is not a part of the sum. So when we specify this is a 4-bit adder, so when we specify a 4-bit adder, the input numbers are 4-bit wide, but so is the sum. It has to be 4-bit wide. So that one extra carry is what we call carry out. Okay, it is useful in some cases. For the most part, at this point, we're just going to say, okay, this is the extra carry. Okay. The carry in, which is this bit here, is an input pin. And for now, you know, we usually just assume it is 0 because, you know, this calculation is standalone. So now the question is, when do we need to attach the carry out to the carry in? If you're only given a 4-bit adder and you want to perform, let's say, an 8-bit addition, how are you going to do it? Yep, you basically want to stack them up side by side so that the carry out of the least significant 4-bit becomes the carry in of the most significant 4-bit. That is when, you know, the carry out and the carry in become really important. Yep. Back there.
What happens if you put that to a 5-bit adder?
What if I?
So that addition, what if you perform that calculation on a 5-bit adder? The carry would then become part of the sum.
But then it will also have its own carry out. In other words, you know, it doesn't matter how wide the adder is. There's always an extra carry bit to the most significant side to remember, basically, do we have an overall carry after this entire addition? Is that okay? Or
so that extra carry bit, since it's only 4-bit, that would be the carry out for the 4-bit. But if it was in a 5-bit, wouldn't that carry be part of the actual sum?
if it's a 5-bit adder, then you would have 5 bits as the input numbers, 5 bit for the sum, and then you will have one extra carry bit over here. Now it may not have a value of 1, but there's an extra carry that you have to specify.
So my point was that if you perform this calculation on a 5-bit, then the sum would be 1110 and not 110. Right?
Okay, so there are two concerns here. If you're dealing with a 5-bit system, then -1 is no longer 1111. -1 is going to be 11111. And -2 is going to be 11110. So that means the result is going to be 11101 with an overall carry as well. Is that okay? Okay. So if our main concern is, does the addition circuit work on negative values that we want to represent? The answer is yes. This example is supposed to illustrate the fact that we can use exactly the same adder, but this time we're dealing with the addition of negative values, but represented in a binary fashion. So is that okay or not? Okay. All right. Yep.
So when you have a carry and it's signed, unsigned, is it considered overflow, or we won't talk about it?
That's a good question. So after an addition, if you already know that you're dealing with unsigned values, if you set the carry flag, it means you have overflown what your number can represent. The result of the addition is more than what your bit numbers can deal with. So that is correct.
So what does it mean when you have a carry bit and it's signed? Or
It does not mean a single thing when you have signed values. So that's a good question, but we are not going to talk about it until we talk about comparison. Okay. So the significance of the carry bit or the borrow bit, to be more specific, has to do with comparison. So right now we are only using it so that we can chain longer and longer additions. So are there any additional questions about this particular example? Nope. Okay, all right. Okay, so let's see. We're gonna go to the new slide here. And we're gonna go back to the notes too, because I want to show you where we are at this point with the notes. So at this point we are done with binary subtraction, and we are moving on to signed value representation. Okay, and my computer ran out of juice last time, and that's why part of the lecture was not recorded as a result. Right. So the idea of a number circle is already illustrated. And then there's the question of which value is 1111 as a base 2 number representing. Is it representing 15 or is it representing -1? And the answer is we don't really need to know until it is used for comparing. Okay, when we use it for comparing, then we really have to know, because if you're dealing with signed, then 1111 is representing -1, and it is less than 0000, which is representing the value of 0. If it is unsigned, then 1111 is representing 15, which is greater than 0000, which is always representing 0 itself. So it's only when you compare that we really need to know, are we dealing with signed or unsigned? Okay. So now we're going back to arithmetic negation, and the general idea is how do we perform negation? Okay. One thing that we usually do not talk about, but it is actually true, is when we perform, so forget about this equation for now, okay? When we perform addition and when we store integers, they're not really integers. And we're not actually doing pure addition or subtraction. We're doing everything modulo something. And that has to do with the range of values that integers can represent in a computer. Not the mathematical definition of integers, but integers as a type in C and C++. So I'm going to show you the range, okay? So, okay, switch back to this tool. So let's say we are given n bits. In other words, n can be 32 for the previous generation of processors, 64 for the current generation of processors, and 128 for future, for the next generation of processors. Okay, so typically n is a power of 2 itself, but doesn't have to be. If you are looking at unsigned integers, then the values will range from 0, which is natural, right? Because 0 is the least unsigned value that you need to represent. and then it goes up to 2 to the power of n, and then the entire thing minus 1. So just to emphasize, I'm putting parentheses around 2 to the power of n to emphasize this minus 1 is outside of 2 to the power of n. So when n is 3, what is the largest unsigned value that I can represent? 7, because 2 to the power of 3 is 8. 8 minus 1 is 7. Okay. What about signed integers? When you're dealing with signed integers, then you are going from negative 2 to the power of n minus 1. So this time n minus 1 is in parentheses, which means the entire thing, n minus 1, is the exponent of 2. This is the most negative value that you can represent. 2 to the power of n minus 1. Once again, I'm using extra parentheses here to emphasize that n minus 1 is the power of n, the power of 2. But then we also have a minus 1 on the outside. Now this minus 1 on the outside has to do with 0. It's also a non-negative value, and that's why 0 is taking up one spot on the non-negative side, and as a result, the most positive value of a signed number seems to be 1 less than what it should be. Is that okay? Is that consistent with the number wheel that we saw earlier? The number wheel is representing 4 bits, right? So according to this, negative 2 to the power of 3, which is negative 8, is the most negative value that we can represent. Yep?
Why they decided to do more negative than positive?
No, they're equal numbers, okay? Our focus is negative versus non-negative. 0 is non-negative.
Oh.
So
But
they
it's
are,
not
so,
positive.
huh?
I said, but it's not positive.
Well, okay, so that's a good question, because if you ask a math professor and ask, is 0 positive or negative, the math professor would probably say it is both, or it is neither. Okay, there's no, it's symmetric. Okay, if the professor says yes, 0 is also positive, then the professor will have to say yes, 0 is also negative. But in computer science, it is not. Okay, in computer science, 0 is considered a non-negative value. So that's why it takes up one spot on the non-negative side, and that's why we have this negative 1 or minus 1 when we need to work out the range of signed values. Yep.
We use zeros in arrays so well.
Well, there's another reason why we use zero-oriented notation, but that will come later on in this class. Yes, go ahead.
But if we were given 3 bits,
Mm-hmm.
negative 2 to the 3rd power minus 7 gives us positive 4. Or is the negative?
Are we talking about signed or unsigned?
Or sign?
For signed, okay. So
the
for
negative
signed-
applies to the outside.
Sorry?
The negative applies to the outside of the 2
Yes.
to the n minus 1.
Yep, you're right. Okay, so just to emphasize, yep. So that's making more clear. Yep.
Would it also be true that it goes from negative to, never mind. The second part, would it be 2 to the n minus 1 divided by 2? Could it also be that?
This part can be, but only this part. This is 2 to the power of n, the whole thing divided by 2.
No, the
Because you're-
whole equation,
Huh?
not minus 1.
This minus 1 has to be here. Because this is telling you the largest positive value you can represent is going to be an odd number. Cannot be an even number. Now if you divide the whole thing by 2, then if you use integer division, then you're not going to get the same result.
Well, because 2 to the power n.
Oh, okay, it's always going to round down, right?
Yeah.
Yeah. Yeah, but this is usually how it is defined, is you subtract 1 from the exponent and then you do the minus 1 on the outside. But I see what you mean. Yeah, because you're relying on the truncation
The full.
property of a integer division.
Yeah.
Yeah.
I guess maybe that's relying on too much.
Right, but this one you don't have to make any assumptions. This is the exact value.
Okay.
Yep. All right. Any other questions? But this is actually important Okay, because every time you use integers or unsigned integers in a program, not in this class, okay, it can be 430, can be, you know, in another class, it can be a programming project, you know, after you graduate and it's part of your job, okay? You really need to be aware of the range of values that can be represented by whatever integer that you choose to use as your variables, okay? Then you will say, you know, well, most of the time, you know, I only need, you know, a very small range, so it doesn't really matter how wide the integer is. Or if the program seems, okay, the worst argument I get, okay, from people who are writing programs is, but it works. And so I don't have to change it. I don't have to refine my program any further because it works. And that is one of the worst, okay, I'm not gonna be judgmental. I'm gonna say, usually it leads to a lot more work in the future. How about that, okay? So I'm only stating the facts and not using judgmental words like wrong or bad or stuff like that. Okay, so the question is, why? Why do we have to be aware of these things from the get-go? Okay, I can give you an example. So many years ago, I was teaching micro mouse design at UC Davis, which is a robotics class, okay? And for the controlling of the speed of a stepper motor, there is an equation that involves the calculation of a square. Okay, square is no problem, right? I mean, it's just a number times itself. No biggie. And I told my students, well, you can write this program on a PC and simulate the stepping, so then you can look at the timing of the steps and make sure that your acceleration is done right, the deceleration is done right, and it does stop, you know, at the right displacement. In other words, you know, you simulate the whole thing, you know, using a PC because it's easier to debug on the PC. You can just use GDB or use the built-in. You can use the GUI, you know, debugging ability of code blocks or whatever, right? And then the program would be ported to run on a kind of like a Arduino type of processor, because, you know, that's where the robot is. Okay, the robot is implemented using a much weaker processor, like the ones used on Arduino boards. And then many of my students encountered a problem. It worked just fine on the PC, but it doesn't work all the time when it is actually on the robot. It works when the displacement is relatively small, but when you try to specify a longer or a bigger displacement or a higher speed, it stops working. And everybody was scratching their head. And then I was going like, so how wide is an integer for the AVR, you know, platform? Because that's an AVR GCC, which is a cross compiler for a different processor. And as it turns out, an integer, if you just say int, is only 16-bit wide on that particular platform. But it is natively at least 32, if not 64-bit wide on a PC. So on a PC, an int, okay, is wide enough to handle all the values that that program needs to handle. But when that program, without changing any source code, is recompiled for a smaller architecture, the 16-bit integer doesn't have enough range to store the values that needs to be stored anymore. And then those programs broke. So if they had used this type of notation, uint64_t, from the get-go, when they were developing the programs on a PC, they would not have those problems at all. Okay? So this is going back to what I said a little bit earlier. Okay? So if the student if I look at the student's program, you know, on a PC and go like, well, you really should be figuring out what is the default size of your integer, and then declare and then use, you know, these notation, uint and then the width of the integer. And then the student is going to come back and say, but it works, right? Well, I'm not going to argue with that, okay? Yeah, I can see your program is working when it's on the PC. But if it is not changed like this, and it is recompiled to a smaller architecture, then the program doesn't work anymore. Now, in hindsight, it's always 20/20, okay? You know, because now we know that's the problem. But at the time, they didn't know. They did not know that the width could have an impact on the logic of controlling the stepper motor, you know, ramping up and ramping down the speed. So they were looking at different things. They were looking at connections to the stepper motors. They were looking at all the wrong places and spending a lot more time than they really should have to fix that one. So this is going back to, but it works is not always the best thing. Okay, programmers or developers really should be aware of these issues ahead of time and not just say, okay, but my program works. Is that okay? All right. Okay, so getting back to the notes here, we are, okay, this is important because what it is saying is, okay, let's just focus on unsigned numbers, okay? This is the range of unsigned numbers. So when you perform addition, it is actually a modulo, arithmetic. It is not just normal addition, which basically means at the end of every addition, it is mod, the largest integer you can store in 64 bits. Is that okay? Or not?
Why is it that?
Because you can only store x number of or n number of bits. Okay, so let me clarify with what I mean by modular arithmetics. So let's just consider addition, okay? And we're dealing with a small, relatively small bit number. So let's say n is 3, okay? So we are dealing with a really small integers, 3-bit wide, okay? So every time you perform addition, so let's say x is a 3-bit number and y is a 3-bit number. So using the notation that we talked about earlier, this is going to be u int 3 underscore t because it's a 3-bit unsigned integer. Don't try this; it doesn't work. Okay, no header file is going to define a 3-bit unsigned integer. But for discussion purposes, this is what I'm doing. So when you say z equals to, so let's say z has the same type, okay? And when you say z equals to x plus y, that's not what it's doing. It's not the entire thing, okay? When you see z equals x plus y, what it really is doing is saying z equals to x, the value of x plus the value of y, but then there's a mod here. What is it going to mod with? What is the largest value that you can represent using 3 bits? 7.
Yeah.
That is modular arithmetics. In other words, whatever is stored in z cannot exceed, oh, I think I just messed up here. That's 8.
Yeah.
It's modding 8. In my mind, I was bitwise ending with 7, which means exactly the same thing as modding with 8, but using the mod operator should be modding with 8. Okay, but when you mod with 8, the largest value after the mod is going to be 7. So if x is 4 and y is also 4, then you have 4 plus 4, which is 8. 8 mod 8 is 0. So z is going to store 0. Is that okay? Yep.
So the mod that you're doing, like, the reason you're picking 8 rather than like 2 to the n minus 1 kind of stuff is because of what you just said, right?
Yep. All right. So are there any questions about the limited number of bit aspect and how it impacts what value can be stored, and also what seems to be a very simple operation, which is addition, actually has a hidden mod operation right after that. Every single operation has a hidden mod operation after that. Is that okay? All right. So at this point, our focus is now shifted back to how do we perform negation. In other words, in arithmetics, negation is easy. Okay, in the math class, and you ask your professor, how do I negate a value? Okay, if you're given the value x, negation of x is just a minus sign in front of x, right? That's pretty easy. But we don't have that kind of operation in computer science, okay? Because no gate is going to do that. So we have to translate everything back to gate operations. And the question now is, if I have a certain value and I want to look at the flipped, the negation of that value, what do I do to get to the negated value? That's the question. Okay? Some people already know the answer. It's called 2's complement. Okay? But let's not look at 2's complement. What we're going to do is we're going to go back and look at the number wheel. Because when we look at the number wheel like this, then I will ask you guys to figure it out. Okay? If 3 is over here, it is represented by 0, 0, 1, 1. How do we get to the representation of the negation of 3, negative 3, which has a representation of 1, 1, 0, 1, which so happens to be the value of, which happens to be the representation of 13 as well. Okay, so what do you think? Can we do this using some kind of arithmetic operations? Subtraction? Okay, what are you subtracting?
I could just be thinking of that 1 and A1, but don't you just, so you have 4 bits, you take 4 zeros and then add a 5th bit of 1.
Okay, go ahead.
So are we trying to change the binary representation of 3 to the binary representation of negative 3?
Yes.
What if we do like the, what is like the squiggle where it changes the bits from 0, zeros,
bitwise or?
and ones to 0?
Bitwise not.
Yeah, and then you add 1 at the end.
Yep, that's 2's complement. Okay, but it is actually there's a pattern here. Do you see that 15 minus negative 1 is 16? 14 minus negative 2 is 16. 13 minus negative 3 is also 13, and so on. So that means, if we subtract whatever value we want to flip the sign from 16, we get the representation.
One more time.
Well, we'll actually carry out the operation, okay? So let's say you're dealing with negative 5. We want to negate 5. 5 is the value that you're given with, and you want to find out, okay, what is the negation of 5? What is representing negative 5? All right? So when you look at the chart here, okay, you go like, okay, I know where 5 is. But when you say 16 minus 5, whatever is representing 16 minus 5 is also the binary bit pattern for negative 5. Okay? So 16 minus 5 is 11. But the bit pattern of 11 also is the bit pattern of negative 5. In other words, you subtract the bit pattern that you want to negate from 16, you get the negation. Does it work the other way around? If I give you a negative value and you apply this trick, do you get back to the positive value? Well, let's check it out. Let's try negative 3. Okay, you start with negative 3 and you say, I'm going to apply this trick here. 16 minus negative 3. You go like, oh, that is going to exceed the whole range, right? Because this becomes 19. But remember, everything is mod 16. So when you say 19 mod 16, what do you get? You get 3. Is that okay? So that seems to work. Just subtracting from 16 will work. Yep.
If it were more than 4 bits, would you just do like subtract it from 2 to the n?
Yep. But we have a minor problem here. If everything is 4-bit-wide, so is your subtractor. What is the problem with trying to subtract something from 16 when the subtractor is only 4-bit-wide? 16 cannot be represented using 4 bits. Okay, so how do we fix that problem? Okay, so now what we want to do is to say 16 minus x, whatever is the value, is representing the negation of x. Okay, x is represented as a binary number. But we cannot do the 16 minus x for a 4-bit system, because 16 as a value cannot be represented using only 4 bits. Is that okay? can 4 bits represent 15? Okay. So we can do that. Yes?
Yeah.
But then you go, attack, you're off by 1. Can we do that? And I can rearrange the operations. So instead of saying 1 plus 15 is 16, 16 minus x is what we want, we just say, okay, let's do the subtraction first. 15 minus x. I can do that with a 4-bit subtractor. Whatever that thing is, add 1 to it. And you go like, okay, but how does this have anything to do with 2's complement? What do you think 15 looks like as a 4-bit number? It's 1, 1, 1, 1. Okay? So now we say, okay, this is 1 plus 1, 1, 1, 1 in base 2 minus x. What is so special about it? Well, in order to understand why this is kind of really, really cool, let's look at the subtraction in the long format. Okay, so we are subtracting x from 1, 1, 1, 1. But x is a 4-bit number, right? So we're going to go back to the notation of x0 means the bit 0 of x, x1 means bit 1 of x. So now we have x0, x1, x2, and x3. Is that okay? What is so special about this? Okay? Do I have to worry about borrow in this case?
No,
We don't have to worry about borrows. Why not?
because we've already reached the maximum that our 4-bit system can hold.
Yep.
We're subtracting from that.
You can also look at it from the perspective of the borrow function. Remember, the borrow function is the negation of the first and the non-negative version of the second. Well, we are looking at the negation of ones. It doesn't matter which column you're looking at, we're negation 1. We're negating 1. What is the negation of 1? 0. 0 and whatever is 0, which means there's no chance we can actually have a borrow. Okay, then what is so cool about this? What is the range of value of x0, x1, x2, and x3 individually? It is 1 bit, right? Each one is only 1 bit. What is the range of value I can represent when I only have 1 bit? 0 or 1. Okay. What is 1 minus 0? 1 minus 0 is 1, which is the opposite of the 0. What is 1 minus 1?
0.
Which is the opposite of the 1. Okay. So that means I can now say this is the negation of x0, this is the negation of x1, this is the negation of x2, this is the negation of x3. Does that work? This is a really important part, okay? Does that work?
Yes.
In other words, instead of using a subtraction, I'm only doing a bitwise NOT. This is exactly what bitwise NOT does.
So it's like exclusive. Exclusive OR.
Not exclusive OR. This is bitwise NOT, which is a unary operator. Okay? So after this, we can now take this equation over here and say, oh, this is the same thing as bitwise NOT of x, which in C and C++ uses the tilde symbol. And for those of you who said 2's complement, does that look like 2's complement to you? Bitwise NOT plus 1. And this is why 2's complement works. I don't want to just define what is 2's complement and tell you that, okay, it works. I want to tell you why it works. I want to tell you how it is derived. Yep.
Maybe I'm kind of spacing here, but what is bitwise NOT?
Bitwise NOT is exactly that. You take every single bit position. Yeah, it's
Oh,
very good timing there.
and then you just
Yeah, so you take every single bit and you just flip it. You
Okay.
flip it on a bit by bit basis.
Okay.
Can we build this circuit? If you have an adder, you can build a circuit. You can actually do negation. Do you guys want to see me do it?
Yeah.
see me sweat, going like, oh, why is this connection going to? What gate should I use here, right? Okay, so let's see. Java, that's jar, and then Logisim is probably somewhere here. Yep, there we go. Okay. So we got Logisim. And how many bits do you guys want to deal with? 4 bits is 5? Why 5? Because we don't have a circle for 5, so we're familiar with the 4-bit one. Okay, so we'll deal with 4-bit. Okay. So here's a 4-bit. Okay, data bits to 4, and we'll just call this x. Okay. The output is going to be on this side here. We are going to call this the negation. Whoops. The negation of x. Whoops. The negation of x like that, and it's also going to be 4-bit wide. All right. So now what I want to do is to convert this equation here, or this formula, this expression, into gate logic, right? Well, which one should I do first? The plus or the bitwise not? Bitwise not. Okay. So we go back to Logisim, and then we go to gates, and then we pick out a NOT gate, which is negation. The NOT gate is natively 1-bit wide. We just have to increase it to 4 bits. So now we are, okay, let me magnify a little bit more. Okay, there we go. Okay. There we go. Line up. There we go. All right, so you can test this already, okay? In case you haven't noticed, you can actually use the poke tool to click on something to find out what the value is. So if you click here, oh, I guess you have to make it a wire first. Okay, so we'll make a short wire like that, and now it should work. So if you click on the wire, it tells you, what is the bit pattern. But it's also telling you a negative value here. Your previous lab has that, right? That turns out to be the signed, it turns out to be the value of the signed interpretation of the bit pattern. Is that right? I mean, 1111 in that circle, do you remember? Was that representing -1? Okay. Yep. So that's really cool. So now I'm gonna cheat. I'm not gonna make my carry look ahead 4-bit adder here, because that's gonna take a little bit of time. So I'm just gonna cheat and pull out a adder here. There we go. Okay, so here's my adder. So the adder has 5 terminals. It's got 5 ports. Carry in, carry out, the 2 numbers that you're adding, and then the sum. Okay. So this one is pretty easy, but I do have options. Okay, so I'm gonna show you guys how to do this, but with a very kind of interesting option to do it. The adder is going to be 4-bit wide, so that's why it's complaining. And you can also specify constants. Constants are interestingly under wiring. So under wiring, you can pull out a number, a constant, and I'm going to put a 1 here, and I will put a 0 down here. In other words, I'm adding 0. And this has to match the width as well. And this is going to be the value of 0. So I'm adding the negation of x to 0, but I'm specifying the carry in to be a 1. That's the same thing as adding 1. Okay, carry in is your k0, which allows you to add that 1 extra, which allows you to specify and add 1 just by specifying a 1 for your k0. Yep.
So if you're adding more than 1, you just put a different number in there, or?
If you're adding more than 1 and it's a constant, you can just change this one back to 0 and specify whatever constant you want to add here. But right now I'm just adding 1. Okay. So now we pull this wire and say, am I looking at the negation of 0? All right. That's a trick question. What is the negation of 0? Negation of 0 is 0. And how do we represent 0?
0, 0, 0, 0.
Okay, well, let's see. That works. Okay, so before so I'm gonna use this, connect my output pin to the wire, just so that it shows the result all the time. Okay, so now we can play with this. What other values do you want to specify and check out the negation and see if it works?
4 bits, so -7.
-7? Okay. So -7 is going to be 1, 0, 0, 1. Okay. So we got 1, 0, 0, 1. Okay, so it spills out some bit patterns, and we are not even sure that 1, 0, 0, 1 is the binary representation of -7. How do we check it? Well, you guys know it already, especially if you're from the early lab. The poke tool, right? So you poke the wires. You poke this wire, it shows you what the bit is, what the bit pattern is, but it also shows you the assigned interpretation of those bits. So this is showing us that 1001 is a 4-bit number, has a signed interpretation of -7. It is representing -7. Yep.
Is there a way we can get it to show us the unsigned representation?
Oh yeah. Yep. I can show you how. Okay. But we want to finish the experiment first because we want to make sure that this is actually 7.
Wait, so by default, it always shows the sign bit
Yes.
representation.
So if you want to change this, and I suggest you not to do that until we actually need to change that, because to do your lab, you need the signed interpretation, which is the default. So you go to Preferences, and then you go to, I cannot remember, Layout. Yep, I think it's under Layout. So under Layout, you have first radix when wire hooked. So that's why you see the binary number first, because that's the first interpretation. And then the second radix is signed decimal. But you can change it to any one of these. So you can change it to hexadecimal, unsigned decimal, octal, or binary again. But why would you use two binary? So it does allow you to kind of play with this, okay? And I remember one person somehow had this default changed. And that person was showing me the outcome, and go like, it's only giving me one single thing, where's the other one? So this is a pretty useful tool, okay? Because you can debug a logic gate design by poking the wires. Then you can figure out, okay, what is the content on that wire? The content of this wire is representing -7 as a signed interpretation. The content of this wire is representing 7. The content of this wire is 0. This is 1. This is 6, and so on. Yep.
What if you change the
What if you change
the CN?
the CN?
Probably won't matter to the answer.
Well, what are you changing it to? Okay, so you're changing the carry in to 0, then it will just be a bitwise not. Because you're adding 0 to the bitwise not, so now it's just the bitwise not. But then you can also change this back to a 1, then we're back to 2's complement. Mm-hmm.
And with that, so with the 1 and the 0, is the 0 just present because it requires all of those inputs? And that there has
Which
to
one?
be, now it is the top 0.
Oh, you mean this one, the carry in? Okay, so as a general rule, you do not want to leave any input pins unconnected.
Yeah, that's kind of what I was thinking.
That is the reason.
Okay.
That also applies to logic gates, even though the manual specifically say that if the input of a logic gate is not connected, it is just not used and it's okay, it is safe. Generally speaking, you don't want to rely on that assumption or that rule. Okay. Okay, so now the question is why? Okay. Every time I explain something, I want to kind of tell you why, because otherwise it's just a rule and there's no particular reason to do something specific. Okay, so let me switch back to the tablet here. Okay, so let's say this time you're actually designing a circuit on the circuit board, somewhere on the motherboard, right? Okay, and here's your IC or integrated circuit, and it's got pins and stuff like that, okay? And let's just look at this pin here that is, for whatever reason, okay, you think this pin is not used, okay? It's an input pin, and I'm not going to connect it to something, because in cisp310, logic sim says if something is not connected, it's perfectly okay, right? So you carry that assumption to actual circuit board design, and you go like, well, this chip is implementing a 4-input AND gate, of which I only need 2, so I'm going to leave 2 of those inputs unconnected. Logic sim says it's okay. Okay. So it's not connected, but it's basically a wire, right? Because even though you don't see a wire, internally the chip or the silicon or the transistor area is really, really small inside the chip, especially when you're dealing with AND gates and stuff like that. The transistor portion is really, really small. But all the pins on the outside needs to be connected to the appropriate port on the inside. So you have a conductor that is kind of short. We're probably measuring in multiple millimeters, okay, 5, 10 millimeters or something like that. But nonetheless, it is a wire. And it's a wire that is floating, which means nobody is really telling this wire whether it should be high or low voltage. It's just what we call floating. So if the wire is floating, what is it going to do?
Who knows?
This is a physics problem.
Crosstalk, whatever the wires around it.
Okay, so there are things that can affect it, right? Okay, so how can it affect a wire that is left floating and is not doing a single thing? At least it appears not to be doing a single thing. So if there are wires around it and they are doing all kinds of stuff, why would that affect this particular wire? What is that effect called? It starts with an I. Inductance. Okay, inductance. So you can induce a voltage potential on this wire. What else do you think can induce a electrical potential on that wire? Outside? What is going on the outside? The cell phone. When the cell phone rings, okay, it actually emits quite a bit of interference. Okay? Or your microwave. Oh, your microwave oven is really powerful. It emits a lot of interference. Even with the door closed and everything is quote unquote properly shielded, it is still a source of interference. Just ask my son. Because his workstation, okay, whatever you call that, his computer is really right next to the microwave or really close to the microwave. And every time, my daughter, microwave edamame or something, my son's going like, oh, look at the lag. He's playing League of Legends, right? And his lag time is like 5,000 milliseconds. Yep. And that's because of the interference coming out of the microwave. Okay? So when you have a design like this, you have a wire that is not connected and it's going to the input of something. It is going to fluctuate all over the place. Okay? Is it a 0 or is it a 1? It depends on many things. Did you turn on the microwave? Is your cell phone ringing? Is it a blue moon? Okay? The phrase, once in a blue moon, now we actually understand what it means. I think it's like 2 days ago, right? The blue moon? Yep. All right. So, did I explain why you should never leave an input pin unconnected? Because if you do not specify something, then in the interference will specify something. So you always hook it up to something. What if you absolutely have nothing to connect to this pin here? Okay, then it depends on whether it's an OR gate or an AND gate, right? So if this is an AND gate, okay, so if this is an AND gate, then you go like, well, I don't want this pin to really affect anything, so what value should you specify? A 1, exactly. So in general, okay, you want to connect this to what we call the power, because power means 1. But this is also a bad idea. This is also a bad idea because if this pin for whatever reason if this chip is bad, okay, and it is actually trying to drain everything to ground, this is going to be bad for the circuit board, okay. So what you typically do is you use a pull-up resistor like this, and the pull-up resistor can be fairly large, okay. We're talking about 10 kilo ohm or something like that. So this way, you don't need a lot of current to put a voltage on this pin, because it's like what we call high impedance pin. If it's an input pin, it's typically high impedance. What is impedance? It's kind of like resistance, but applied to AC circuits, right? So this circuit has a high impedance input, which means it needs a very small, really tiny current to pull the voltage of this pin to whatever the supply voltage is. But if you use a pull-up resistor like this, and for whatever reason you saw the wrong chip, for instance, or the chip itself has gone bad, and you want to ground everything possible, at this point, it's not going to hurt anything, because that connection is going through a 10k ohm resistor. If your supply voltage is say 5 volts, then you're really talking about less than a milliamp going through the whole thing. It's not going to hurt anything. So all of these are kind of like for safety purposes. You put in the pull-up resistor. You do not need anything unconnected. La 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 la. How many of you are planning to become a electrical or computer engineer? So you'll hear this kind of lecture again. The rest, it depends on whether you make a transition later. I learned all these things not from a class. I learned all of these things as a software engineer. And you guys would go like, how come you have to learn all of these things as a software engineer? Don't you just kind of write code and debug stuff? Well, I was the software engineer for a embedded system firm. What are embedded systems? Arduino, Raspberry Pi. So what makes those things embedded? They're called embedded computers. Embedded means the computer is not seen. There's no user interface to the computer itself. It is hidden inside some other machinery. Is that okay? So the company would design these circuit boards. The hardware engineers or the electrical engineers would design the boards. And then they would drop it on my lap and say, Tech, make it work. Do your magic, make it work, make it tick. And many times, it won't tick, okay? Because the hardware is not designed correctly. Okay, they're missing a pin, or they do something like this, having a floating pin or something along that line. So it doesn't work. But everything I do in software is already making the assumption that certain parts, has to work. So when it doesn't work, and they keep insisting that it is me that is making it not work, then I have to learn about circuitry, how to read schematic and stuff like that, so I can go back to the electrical engineer and go like, okay, see this pin over here? See the equation of that pal over here? This is why it's not working. This is how you fix it. Yep.
So when gal, or like when you said don't leave any inputs unconnected, so is the general rule of thumb to connect a 0 or a 1 chance?
It depends on whether it's an AND gate or OR gate. If you're dealing with an AND gate that has way too many input pins and you don't need all of those, then you have to connect a 1. Because 1 is the identity of conjunction, so you can hook up you can hook up the input of an AND gate to 1s and not affect the result of the conjunction. If it's an OR gate, you have to connect it to ground or 0, because 0 is the identity of disjunction, so you can hook up as many zeros as you want to the same disjunction or OR gate without affecting its calculated result. All right. Okay, so I digressed. Are there any questions about this particular circuit? It is 2's complement. It is adding 1 to the bitwise naught of the original number, but what the purpose that it serves is to flip the sign, but preserve the absolute value. Is that okay? Yep.
What's that one, the purpose of that?
Which part are you?
Well, what's that constant?
This one?
No, the constant.
This one?
Yeah.
It's just a constant going into one of the inputs of the adder.
So when, the last time you finished the topics, the carry is
That's right.
1, and then the was constant is 0.
Yeah, so it only one of these two has to be a 1, the other one, 0. It will serve the same purpose.
Do we need that 0 for the first circuit?
Huh?
Do we need that constant?
For which circuit?
The first one you put as the 1 on the top and then the 0 on the back.
Okay, this is carrying, which is serving the same purpose as K0 in your circuit. So K0 is just one of the things that you're adding. So, okay, so when you're dealing with an adder that has two numbers and a carry in, you're adding three things. You're adding the two numbers and the carry together. So the carry is really a part of the addition. It's part of the numbers that you're adding. In other words, the sum in this case is this plus this plus this. If the objective is to add one to whatever this is, you can specify the 1 here and put a 0 here, or you can flip and specify a 1 here and a 0 here. Either way works. Yep.
Would it be bad practice to have the output since you have 4 bits of input going in, and there's a carry, would it be bad practice to have 5 bits of output and then just so that way it will reflect the carry bit in one instance instead of having the separate carry?
You do not want to increase, you don't want the input width to be different from the output width. So the extra carry is its own pin. Usually it is not a part of the result. And that's why, in this particular adder, carry out has its own output, has its own port, and then the sum, is a different port. Is that okay? Yep.
Okay, so can I ask you about the I lost the question.
Oh.
It doesn't work.
Okay.
Sorry,
It's okay, happens to me all the time. Yep.
It's kind of a logic question, but
Mhm.
like how these gates and arithmetic operators, you can specify the bits. Is it that there is some tool in there that lets you specify, or is it that they're kind of just hardwired and to tell whether certain amount of bits and just stop?
I'm not quite sure what you're asking.
So like how you can make that adder 1 bit, 2 bits, 3 bits, 4 bits.
Right.
Is there a tool in Logicin that allows you to make your
Oh, unfortunately, this is hardwired. So
Okay, it's
it is
hardwired.
manually specified. It cannot be specified by another component.
no, that's
Yep. Yeah. So that part is difficult to do. Yep.
So I was gonna say the two's complement works only from negative to positive, but not from positive to negative, or works.
Well, let's check out this circuit then. Give me a positive number that you can represent using 4 bits.
3.
Would that work? Do you want to use 3?
Yeah.
Okay. So we will specify 3, which is 0, 0, 1, 1, right? 0, 0, 1, 1. And we'll double check, okay? Is 0, 0, 1, 1 actually representing 3? Yes. Ding. And what is the negation of 0, 0, 1, 1? It would be 1, 1, 0, 0, right? What is the value represented by 1, 1, 0, 0? Do you remember that number wheel? How many times do we have to click counterclockwise in order to get to 1, 1, 0, 0? You click once, it's 1, 1, 1, 1. Click twice, it is 1, 1, 1, 0. Click 3 times, it is 1, 1, 0, 1. Click it 4 times, it is 1, 1, 0, 0. So what do you think 1, 1, 0, 0 would be representing? In other words, when I click this wire, it will show 1, 1, 0, 0 as the bit pattern because it's just a bitwise knot. But what is the value it is representing that is using the sign interpretation? -4, because we have to go from 0 and then we click 4 times counterclockwise on the number wheel. So let's click, making sure that is the case. It's all good. And then -4 plus 1 is -3. So that's why it works. So the input of this entire circuit is 3. The output of the entire circuit is -3. So it works. It also works for positive number as input, and then you get a negative number as the output. Yep.
So, but does it not make it -3, and -3 plus 1 would be -2? Or the not doesn't flip the sign?
Okay, so after the not here, this is 1100. 1100 is -4, not -3. And that's why we have to add 1 to make it -3.
So I always have to add 1 to flip the sign.
Yes, that's how 2's complement works. Yep. But the rationale behind 2's complement has to do with this trick that I was trying to illustrate here. So the trick is, we know 16 minus, with 4-bit numbers, 16 minus whatever the value we want to flip the sign of works. But it doesn't work when we only have 4-bit subtractors. So the trick is separating the 16 to 1 and 15. So we perform the 15 minus first, and then we add 1 later on. But 15 minus something turns out to be just the bitwise not of that something, because we are subtracting a bit from a 1 all the time. So we are really just inverting the bit, the individual bits, and that's why it becomes 1 plus the bitwise not of the bit pattern, which is also called 2's complement. If this is called 2's complement, if the entire operation is called 2's complement, can anyone guess which sub-operation is 1's complement? The bitwise not, exactly. So the bitwise not, which is this part here, is also called 1's complement. But when you add 1 to 1's complement, it becomes what we call 2's complement. Are we doing okay so far with this? All right. I'm just, yeah.
Did you say 1's complement?
1's complement is bitwise not. I think that's explained in the notes too.
1's complement still has to add 1 to it.
Say that one more time.
Because 1 is 1, and if you flipped it, you would get 1, 1, 1, 0, and that would still, you would need to add 1 to get -1.
Right, so 1's complement by itself is not enough to be used for arithmetic negation. You have to add 1 to 1's complement in order to perform arithmetic negation. But 1 plus 1's complement is also known as 2's complement.
So it's just the name.
Yeah, more or less. So are we still doing okay so far with this? Okay, all right. So switch to the notes, moving on. So this stuff, is just what I talked about earlier, how we use a 16, because 1 followed by 4 zeros is 16. And that's the entire slide. This slide, is all done. This module is all done about, how we represent negative values. Do we have any questions about how we represent negative values? No? I'll take it as a not yet. Okay. So if you do have questions, don't hesitate to ask. The next slide talks, or the next module talks about comparison. So now, whether something is signed or not is really going to become important. Okay, so when you click on this module here, and it goes through a whole bunch of math and stuff like that, so go ahead and read this, after the class or before the class. But what I'm going to do is I'm going to just show you the calculations using the tablet. Okay. How do you compare? Given what we already have enough knowledge for comparing. How do you compare? So let's consider signed numbers first. Okay. With all the circuitry that we have already talked about, we already have enough circuitry to compare signed numbers. So how would you do the comparison with signed numbers? So I'm going to claim that subtraction is all you need, and we have subtraction already. Okay. So I'm going to claim. Okay. So we'll do some examples. 3 versus 4, 4 versus 3, and we'll see what happens to the binary subtraction of these things, and we'll use 4-bit representation. 0, 0, 1, 1 minus 0, 1, 0, 0, and we'll go through the entire thing. 1 minus 0 is 1. 1 minus 0 is 1. No borrow in this case. 1 minus 0 is 1. 1 minus 0 is 1. No borrow. 0 minus 1 is 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is 0. 0 minus 1 is 1 with a borrow. Is that okay? Does that make sense? 3 minus 4 is supposed to be negative 1. But if you look at things from the unsigned perspective, 1, 1, 1, 1 is representing 15. But we have an overall borrow. How much are we borrowing? 1, 2, 4, 8, 16. We're borrowing 16. In other words, I got 15, but I owe 16. So the net amount is negative 1. So it does work out. Let's check out 4 minus 3. So we got 0, 1, 0, 0 minus 0, 0, 1, 1 in this case. 0 minus 1 is 1 with a borrow. 1 minus 0 is 1. 0 minus 1 is 1 with a borrow. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0 with no borrow from either subtraction. 0 minus 0 is 0. 0 minus 0 is 0. And we have an overall borrow of 0. Okay, so looking at these two examples, okay, do we have a flag of some kind? Is there a single bit here that can tell us the ordering of the two numbers that we are subtracting? Yep.
The carry.
The borrow or the carry, exactly. They're usually called the same thing. You know, most people just call it the carry, but in a subtraction context, we can call it borrow as well. So the borrow flag is sufficient to tell you whether the minuend is less than the subtrahend. So unless you refer to those terms a lot, some of you probably have forgotten what is a minuend and what is a subtrahend, right? So for that, and I cannot trust my own memory for this type of thing, so we're going to look up minuend and subtrahend. And here we have the definitions. There we go. So in a subtraction, you know, the number that is being subtracted is called the minuend. The amount that you're removing from the first number from the minuend is called the subtrahend. And the result, of course, is called the difference. Is that okay? All right, so are we clear on the terms? Minuend is the first number, subtrahend is the second number in the subtraction. Okay, so getting back to my notes then. Ooh, getting back to here. So I'm claiming that this borrow flag is a 1 if and only if the minuend is less than the subtrahend. Okay, let me put it in writing. Okay. So we are saying that the overall borrow is a 1 if and only if, not just if, not just only if, but if and only if the minuend is less than the subtrahend. Oops, subtrahend. Okay. That's my claim. Does it make sense? Intuitively, does it make sense from the unsigned perspective? Forget about signed numbers, okay? Right now we are only dealing with unsigned interpretation. Does that make sense? If you have a borrow of 1, that means you didn't have enough. It makes sense, okay? Well, just because intuitively it makes sense doesn't make it right or doesn't make it true. So what we'll do is we're going to take a look at the proof. I'm not going to explain it. There's no way I can explain that in 5 minutes. But I'll show you where to find it. It's part of my notes, so it would be in one of these things. Nope. Okay, I cannot remember where I put it. Let me close the ones that I don't need. That's 440 stuff. 440 stuff. I need to have one profile per class because I'm losing track of all this stuff. Okay, there we go. Nope, this is the one. This is the one before. Okay, where did I put my?
The overall borrow represents the sign then, right?
The borrow flag indicates whether the minuend is less than the subtrahend. So subtraction can be used for comparison. It's just that after the comparison, after the subtraction, how do you know the result of the subtraction? The comparison, the answer is you use the borrow flag. Okay? Okay, so here is this is the module that I want to refer to, and the proof of using the borrow flag to indicate whether the minuend is less than the subtrahend is this math here. Okay, so this part of the math is really just indicating how numbers are represented and so on. So the proof is this entire thing. So for those of you who like to kind of make sure that the math does work out, you can actually follow through all of this stuff here. But for the rest of you who just feel like, okay, can we just go with the intuitive explanation? Yes. Okay, so for unsigned comparison, the borrow flag is a 1 if and only if the minuend is less than the subtrahend. Oh, a whole lot is, that's not really that helpful, is it? Because we can only establish less than. Is that enough for all the other comparisons that we might want to do? What do you think? This is going to be the last part of today's lecture. It will take about 2 minutes. Okay, so getting back to my tablet here. So I'm claiming that less than is the only operator that this particular weird programming language is going to allow you to do. You can only confirm whether something is less than something else or not. Can you live with that?
How do you check equals?
Okay, so we'll go from the hard to the easy, okay? Okay, so if you want to check whether x is greater than y, that's easy. Flip the order, right? Okay, it's not a big deal. What about less than or equal to? It is the negation of y is less than x, right? If you say x is less than or equal to y, it is the same thing as saying, oh, it is not the case that x is greater than y. But if x is not greater than y, then y is less than x. So in other words, on this side, I'm only using logical operators and less than. So the idea is less than all by itself sufficient to implement all of the other relations for comparing? Okay. X is greater than or equal to y. That's easy because we just flipped it so that we have that, right? So we got all the stuff that has less than or greater than in it. Now we get to the easy ones, the equal and the not equal. We're gonna do the easy one first. X does not equal to y. Using only less than. Okay, so yeah, go ahead.
Well, you could say not equal. You could say if x is less than y, or y is less than x.
Yep, there you go. So if we know whether something is different from another thing, can we check whether something is the other thing? Okay, so x equals y is the same thing as the negation of whatever we have on top. Right? And I'll just leave it like this because if you apply De Morgan's law, it's not going to look any prettier. So we'll just kind of keep it this way. If you apply De Morgan's law, you just end up with more knots. But it's not going to get any simpler, so I'm just going to leave it like that. But is this convincing you that if I can have just the circuit for confirming whether something is less than something else, it's enough to implement all of the other types of comparisons? Cool. And of course, everything here can be boiled down to NAND gates. But just do it mind you then. Yep.
So just to double check, like this works for both signed and unsigned, right?
Yes. So all of this stuff here has nothing to do with signedness. It is basically stating that if I can confirm less than, I can implement all of the other comparison operators, signed or not. But at this point, we just kind of say, yep, intuitively, borrow is sufficient because that's the whole idea of borrowing. You don't have enough, and that's why you're borrowing. So that's why it works. So next time on Tuesday, we're going to talk about signed comparison, which gets a little bit tricky because signed comparison involves a little bit more stuff. Okay, so I need you guys to read ahead of me on signed comparison because otherwise the discussion is going to go, it's not going to go anywhere.